In this next chapter 4, I want to talk to you about stability. We have seen in the end of chapter 3 that if we have a feedback, normally negative feedback, that also with negative feedback, there are some conditions that a closed loop system can be unstable. And to avoid instability, we have to find methods to check stability. And this is what I want to tell you. I want to give you some methods with which you can check stability. But before we can do this, we should define stability. Definition. And one very general, very simple definition is the definition using the impulse response. Assume that we have a system and we have at the input our ideal unit delta function, and the response of the system is then the unit impulse response. Let's assume that the system is linear and the system is known as an FFP. The transfer function is given. Then system is stable if and only if G, if we wait long enough, so t goes to infinity, is 0. That is the definition, that if there is an input signal with very short time and very large amplitude, and in ideality the delta impulse contains all frequencies, so you have an excitation of all frequencies of all poles here. So if we excite all poles, then the response is the response of all poles, and if we have stable systems, then this excitation caused an impulse response which ends finally at 0, the same value as you have begun. This is mathematically true, but not easy to investigate, because in lab we cannot produce a direct impulse, and we normally of course we can measure the impulse response, but this is not very practical to do this. And we want to have a mathematical method, for example, to check the coefficients of the transfer function. Can we find a method where we just look on the coefficients of my transfer function to check is the system stable or not? To avoid sometimes the calculation of the impulse response, because calculation of impulse response can be very time consuming. And if there is a method where we can see this with the coefficients of the transfer function, that is much more convenient. Okay, some examples. There is a good picture in my Control System 2 paper, which shows many examples of impulse responses. I will show you this page. First, I show you the right part of this paper. Finally, I will show you what happens here on the left side, which is this time hidden. Here you see a series of impulse responses of systems with numbers. The horizontal axis is time, and the vertical axis is the impulse response. And here you see a signal which oscillates, but the amplitude of the oscillation goes down, and if you wait long enough, then the final value is 0. The frequency of this could be smaller. Also, this is a second example of stability where the amplitude goes down to 0. In some systems, the impulse response has no oscillation, Oscillation means conjugate complex poles. If you have real poles, then we have exponential decrease of the output signal. So also, if the signal goes to 0, we call the system stable. This is an example where the amplitude goes faster down than in number 1. This is an example where the exponential impulse goes slower down than 3. And number 6 is a case where we can say, okay, this is not really stable, but also not unstable. That is a border case between stability and instability. If the impulse response stays constant, and this is the impulse response of an integrator, then this is an intermediate case between stability and instability. If I shift this a little bit higher, then we can say, okay, the same situation is if my impulse response caused an oscillation, if the amplitude is constant. Again, this is the border case between stability and instability. We cannot say this is stable, but we can also not say this is unstable. Instability is very clear what this is. If the amplitude of an oscillation is increasing to infinity large values, or if the exponential impulse caused an increase which is never ending and you lost control. Now this is there are some examples of systems which are stable. The upper cases are stability, lower cases are instability, and some intermediate case. So we want to have some methods where we can use the given transfer function and investigate the coefficients to check this stability condition. But before I do this, I give you two mechanical examples where we can very quickly see stability and instability. Look for a pendulum. If this is a pendulum axis and the pendulum is hanging and there is a mass, if you now give this pendulum an impulse, and you know, okay, after some times the pendulum come to the original hanging position, back to the hanging position. This is a stable system because any change, any impulse, any excitation on the system gives at the end the original final position. So you have either this or that situation. The same mechanical system with this situation is different. If you know, if this is a free axis and this is an inverted pendulum, standing pendulum with a mass, then you know if I give a small impulse to this standing pendulum, then of course this pendulum moves back to the hanging position and will never come back to a stable standing position. So this is a typical unstable situation where this goes down to another position, can never go to 0. 0 is then the vertical position. 0 means starting 0 position. So this is stable. This is unstable. A similar situation is a ball in this pot. If we have here a ball and we give this ball an impulse, then you know the impulse, the position of the ball makes this movement and comes back to the original position. If we do the same with the ball in this situation, you know a small impulse on the ball leads to the fact that this ball is falling down. So this is unstable, will never come back to the original position, and this is stable. With any impulse it comes back to the original position. And here you can see what is indifferent, what is the border case between stability and instability. Here you see the ball. If you move the ball with the impulse, the ball is going to another position, not coming back here, but maybe it can stop at any other position. So this is indifferent. It is border between stability and instability and unstable. Okay, so far these are mechanical examples. I now show you a method to combine the impulse response with the transfer function. So I add now a chapter number, the definition is 4.1, and now 4.2 is called criteria for stability. You can find some information in the workbook on the page 35. And what we assume is the transfer function f of p is known. Now we know the coefficients of the transfer function f of p of the system. Can we now combine this impulse response criteria with the transfer function? Of course we can do this. I will show you how. I want to remember you to a very fundamental statement in Laplace transformation. Note that the Dirac function, the input signal, is in Laplace area, in frequency domain, is a function of 1. We know that the g von t is then in frequency domain is g von p, g of p, and the output, the response of the system, is transfer function multiplied with input signal. Input signal is now 1. And you see, very simple, that the transfer function is identical to the impulse response in frequency domain. So the transfer function and the impulse response have the same coefficients, the same function. The only thing what we have to do is, can we now go back into the time domain to write down the g of t, and this can be done with the following trick. First, I show you that the g of p, which is f of p, is in linear systems, and we talk of course only from linear systems, is given as a ratio of two polynomial functions. Now remember, we have talked about this. In the numerator we have used the b coefficients, and in denominator we have used the a coefficients. But in my paper workbook page 35, in other discussions, especially in the next criteria, these coefficients use the letter c. Doesn't matter. Cn p to the power of n plus, go down to c1 p plus c0 is given. And of course, if we want to convert this back into the time domain, then in my workbook table pages, page 9 to 11, we cannot find this expression. But now we use trick to get some information about the impulse response. The trick is using the poles of this system. Yeah, we assume that we know the poles of the system, then we can use the partial expansion to write this same expression in another form. We use the expression residuum a sub o divided by p minus p infinity 1 plus residual A1 divided by P to the P minus P infinity 2 and so on, plus yeah, I think these coefficients should have the extension 1, 2 and so on, plus down to an divided by P to the P minus P infinity n. What are the P infinity values? These are the poles of the system. And to avoid complicated special cases, I assume that P pulses are all different. You know, the partial expansion method has some special cases. If you have double or multiple poles, then there are different expressions, but the statement is the same. P infinity are all different. I just show you this document. This is true for all cases, but I show you just a very simple step to understand the situation in the special case that all poles are different. Then we have just n poles. Yeah, if the power of the polynomial function in the denominator is n, we have n poles. So we have n of these elements which are added, and you know the Laplace transformation now is linear, so I can now convert each part of the sum individually and add the sum here. So I get the g of t, which is now this symbol means now I go from the g of p into the frequency domain, from the frequency domain into the time domain, and now I can write a1 divided by p minus pole number 1 can be converted into the following expression. I just open the workbook page where you see this. Yeah, if we look on page 9, you see here this is the relevant line 0.1 point B, but not written with the pole situation but with time constant situation. So I divide the left part, the left column, divide this expression by t, and then I get e to the power of minus t over t. Or, sorry, the pole is p infinity 1. P infinity 1. Because, yeah, let's assume table t divided by 1 plus pt is connected to e to the power of minus t over t. Now I divide by t, then I get 1 divided by 1 over t plus p. This is it's the same, and this is called here minus p infinity 1, right? Minus p infinity. So if I write this in the next step, 1 divided by p minus p infinity is converted into e to the power of minus t times p infinity. So with this intermediate steps, I can write now the impulse response in this manner: e to the power of minus t times p infinity 2 plus and so on, plus finally a index n e to the power of minus t p infinity n. Of course, I've made an error. Sorry for this. This negative sign here removes this negative sign, so we have a plus here. So in each exponent we have here now positive exponents. And now we can just check what happens with the g of t, in which condition, in which case this becomes 0. in this case where each of these elements becomes 0, if only one element in the sum becomes not 0, then the system is called unstable. So we have to check these are real numbers. Yeah, in the partial fraction expansion, these elements are real numbers. So these are real numbers multiplied with the exponential function, and so we have to check in which condition the exponential function has a final value 0. This is the case if this pole is real, then it must be negative. In the other situation, if we have oscillations here, if the pole is complex, that cause a sinusoidal signal here, then you have a conjugate complex partner here, and then we can combine both elements with the conjugate complex partners. Then we can show, and I don't want to do this now, you have to believe me that this is true, this becomes 0 as final value if the real part of the pole is negative. So we can just very clearly say that this is 0 if and only if all poles of f of p have negative real part, or all poles must lay in the negative negative p-plane. Okay, let's look to this picture. Yeah, I have changed this word. I've looked into my dictionary. Of course, not lay but lie, or must be located. Yeah, be located. We also can say located. Be located in the negative p-plane. Yeah. Now here you can see the complete picture containing my impulse responses with these numbers, and here you see the positions, the locations of all poles in the p-plane. This is the j omega axis, this is the sigma axis. And for example, this impulse response is caused by poles located here as a conjugate complex pole pair number 1. Number 2 has the same sigma but different frequencies. Number 4 has same frequency but different sigma, so the exponential curve goes faster down. 5 is a real pole, 3 is a real pole, no oscillation. But all these poles from 1 to 5 are located on the left side of the p-plane, has negative real part. Number 6 and 7 are poles which have a sigma, a real part which is 0. So these are the indifferent cases with either a constant signal at the output or a constant oscillation at the output. And pole 8 and 9 have positive real parts, and this is the indication for stability. So what you have to do in the investigation of the stability of a function, try to get the coefficients of the transfer function, look in the denominator, because only the denominator is responsible for the stability, calculate the poles, check the real parts of the poles, and if the real parts are all negative, stable. If only one is positive, unstable. If there is one which is 0, you have the indifferent case. If one is 0 and one other is positive, you have instability. Yeah? Only one pole can cause instability. Okay, this is a first stability check using the coefficients of the transfer function with a big disadvantage. because you need the poles. If you cannot calculate the poles, and there are some cases where you can't do this, then this pole criterion is not usable. Of course, if the C's are given numbers, you can calculate with root finders, with numerical methods, any pole if C's are given as numbers. But if the C's are not given as numbers, if they are variables, unknown variables, then you know the solution of the pole of the zero calculation is only possible if n is 2 or smaller. Then you have the PQ equation. If n is 3, then there is a method, but this method is very difficult and manually not usable. And if n is 4 or larger, it is impossible. There are no mathematical procedures available so that you can calculate the poles of the system. So there are limitations in the order of n. So if n is too large, there is no way to calculate this stability criterion using this pole criterion. So we use another method, which comes now in the next video.